Thank you. So today, yes. Um, so when I stopped yesterday, I mentioned this theorem, which classifies triple of maximum span, namely generic, whatever that means, flag triples, in terms of these triple ratio invariants. So you have three flags. The, using exterior powers and so on that spits out numbers. And the claim is that these numbers classify the flags up to the action of the Lie group GLN. That's this correspondence here. Okay, and so today we're going to prove that. And so we're going to, as opposed to yesterday, today we're going to do real mathematics. Okay. So if you remember a little bit, these triple ratio invariants were obtained by looking at this picture of the discrete triangle, namely the set of integers, non-negative integers ABC whose sum is equal to n. And and we used all the dots here were giving us a decomposition of Rn as the direct sum of the eighth subspace of E, the bth subspace of F, and the cth subspace of G. Okay, so if we look at the picture here, we see that the triangle actually has a natural decomposition into smaller gray triangles, as well as these small white triangles as well. So we're going to focus on the gray triangles. So, so let's focus on this one here for instance. And you remember that, so the dots are points in here, ABC, and then when you have a triangle like this, you see the ABCs at the vertices, they differ from each other by plus or minus one, because the points are close to each other. If you look more carefully, they look like this. Namely, there is you have, if you take the smaller, so over these three vertices, you take the smaller A, the smaller B, and the smaller C, that will be alpha, beta, gamma. And so what you see is that they are of this form, alpha plus 1, beta, gamma, alpha, beta, gamma plus 1, and alpha, beta plus 1, gamma, where alpha plus beta plus gamma is equal to n minus 1 because the sum of these has to be equal to n. Okay. So we have these three. Vertices, and if I take the smallest indices here, namely if I replace A by the smaller one alpha, B by beta, and C by gamma, well, I get a sum here. But because alpha plus beta plus gamma is equal to n minus 1, what I get is a hyperplane. So each gray triangle here determines a hyperplane in Rn. Now the problem with hyperplanes is that they're hard to see. We know how to see vectors, but hyperplanes, it's harder. So there is a trick to understand hyperplanes. We go to the dual space. And so we're going to dualize the situation by pressing yes. So we're going to do some duality. What's making noise like this? So we look at the dual space of Rn. And when you have a subspace of A, you have the dual subspace. So the also called sometimes the polar subspace, or sometimes the orthogonal. That's why I'm using this symbol, actually. I didn't want to use star so that we will understand it's not the regular dual. So it's the space of elements of the dual, namely linear forms, from Rn to R only. It's a typo here. So it's a space of linear forms whose restriction to A is equal to 0. Okay, so that's a subspace. And then you do a little bit of It's my glasses. Okay, we solved one problem. Okay, so easy linear algebra gives you that the dimension of the dual is the codimension of A. That if you take the dual of the dual, the dual of Rn, the bidual has a natural identification with Rn. And if you do that, you see that the dual of the dual is the original subspace. Also, because of the definition, the passing to the dual reverses the inclusions. And it turns a sum. The dual of a sum is the intersection of the dual, and the dual of the intersection is the sum of the duals. So because of that, passing to the dual changes sums into intersections and intersections into sums. Okay, so in particular, if I have a flag, F, I can define a dual flag by taking the dual spaces, except that because it changed the dimension, the order of the spaces gets reversed. So the A-dimensional space of the dual flag, what you do is that you take the n minus A-dimensional space of F and you take its dual, okay? So that the dimension agree, and also you remember that the dimension, the inclusions get reversed too. So you need to go backwards like this. Okay. And then, because it exchanges sums and intersections, you can see that a family of flags satisfies this maximum span property if and only if the dual flags satisfy its minimum intersection property. So we had seen last time that when you have many linear subspaces, there is no good notion of genericity. There are the two competing notions. One is the maximum span property. The other one was the minimum intersection. And this shows you that there is no reason to prefer one over the other, because passing to the dual sends you from one to the other. Right? Okay, now let's go back to what we're trying to do. When we had a gray triangle previously, I showed you that it specifies a hyperplane. And so if you take the dual of a hyperplane, that's a line. So that gives you a line, which is the dual of this sum. And therefore, it's the intersection of these duals. And then if you want to express that in terms of the dual flags, it's also the intersection of the dual flags, but the dimensions get mixed up a little bit. So that gives you a line in the dual space. Okay, now a dual space, well, it's a vector. It's a finite dimensional vector space. It looks like Rn, and now we have lines. And so the idea is that in the picture of the discrete triangle, which was there before, this one before, we have a line associated to each of these gray triangles, and we're going to use these lines as a skeleton, as something we can grab and jump from one line to the other in order to reconstruct so first we're going to reconstruct the dual flags, and then once you have the dual flags, you go to the dual again, and that's going to enable you to get the original flags. Okay, and for that we're going to use snakes. You remember my title? So what's a snake? So you have. So this is the original discrete triangle, and with the gray triangles here. And you remember the gray triangles, they are indexed by alpha, beta, gamma, whose sum is equal to n minus 1. Namely, they are in the discrete triangle corresponding to n minus 1. So a dot here corresponds to a gray triangle here. Okay, so a snake is something like this, where it's a path that starts always at this lower left corner here. That's what it says. So it's a sequence of points in the triangle of the discrete triangle of dimension n-1 or size n-1. And so you always start here, and then you move forward towards the opposite side here. That's what this formula here, the fact that alpha k plus 1 is alpha k minus 1, that's what in both cases, that means you're moving in that direction. And then you can turn left, or you can either turn left or you can turn right. So that means that once you're at a point alpha k, beta k, gamma k, you go either to this point or to that point. And so it looks like this. There is a major controversy here to know whether the head of the snake should be here or there. In particular, I have a big discussion with one of my students, former students, Dan Douglas. We completely disagree. I think I'm using the Fock-Goncharov version here with the head here. Okay, and so the point is that when you have a snake like this, you get a sequence of gray triangles. You see it here. And each gray triangle gives us a line. And so I think it's next slide. Yeah, so when you have a snake, you have this sequence of points, and each point gives us a line in the dual space. And so, and it's not hard to see that this by the maximum span property in Rn or the minimum intersection property in the dual space, it's not hard to see that these lines are linearly independent and define the decomposition of the dual space as a direct sum of lines. Okay, so you have these lines, but actually the snake gives you much better than that because it's going to specify vectors in each of these lines. Namely, it's going to give you a basis by specifying a vector in each line. Now, the base is not uniquely determined, it's determined up to rescaling of all the vectors by the same number. So that's called a projective basis. So a projective basis, it's a basis, but defined only up to multiplication by everything. So, okay, but essentially it's like a basis. Okay, and so we define it by induction. And so to start, we pick any vector in the very first line, the one corresponding to the tail of the snake. And actually, so you have a choice here, there, and that's why we have a choice all along. Namely, if instead of this U1, I took 17 times U1, then all the vectors would be multiplied by 17. So that's where the ambiguity comes from, that very first vector. Once I've chosen this very first vector, everything is going to be uniquely determined. And so let's assume that I have constructed it up to the point in the kth line, and I want to define the vector in the k plus 1th line. Okay, so here is the picture. The snake started in the lower left corner here, and then boop, 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 and then it arrives here at this kth point, and then it could either turn left or turn right. Namely, it could go either to this point or that point. But you know, that means that if I follow the triangles, I was here and I can go to this triangle or to that triangle. And you remember that these two triangles give me lines. Okay, so I had the line LK that I reached, and then I can go either, at the next step, I could go to the left line or to the right line. Okay, and now is the key observation, which is that, so I have three lines. the line corresponding to this, the line corresponding to that, and the line corresponding to that. And these three lines are coplanar. They are in the same plane. And that plane, I told you, no, I didn't tell you. I had planned to tell you that. So I told you that a gray triangle determines a hyperplane in Rn, therefore a line in the dual space. A white triangle, if you do it again, count the dimensions, it determines a codimension 2 subspace of Rn. And so if you go to the dual, you get a plane in the dual space. And that's exactly the plane that contains these three lines here. It's this one here. And it's associated to that white triangle here. Okay, and now something funny, which is not well known, but it should. You can give that to your students in your linear algebra class. If you have three distinct lines in the plane, then essentially you have identification. Once each line gives you an identification between the other two. Namely, if you get a vector, so once you choose a vector in once you choose a vector in one line, it doesn't matter. There are that vector uniquely actually no, you have an identification between the three vectors, the three lines. Namely, once you choose a vector in one line, you have a unique vector in the second one and a unique vector in the third one, so that the sum is equal to 0. Okay, it's a simple elementary fact in the plane. And we're going to take, so now the snake, so when we were constructing the basis associated to the snake, we had defined it up to UK. That was the last one we defined. And so we're going to choose a vector to be one of these. So at the next stage, either I go left or I go right, namely either the snake, yes, goes to the right, left, or goes to the right. If it goes to the left, I take this vector in the left line. And if it goes to the right, well, I could take this vector in the right line, but to get the signs right, I put a minus sign here. And don't trust me blindly here, because I've been changing the conventions enough. Hopefully, I made an even number of mistakes. But it's something like that. So the signs could be wrong. It could be the minus sign should go here. But it's the idea. The idea to get the next, to get a result two slides later. Okay, so the upshot is that whenever there is a snake like this one here, it defines essentially it defines a basis for the dual space. Okay, now there are two nice snakes. There is the bottom snake at the bottom of the triangle, and there is the top snake at the top of the triangle. And what you can see is that so the bottom snake corresponds to the sequence of gray triangles at the bottom, and the top snake at the top. And each of them gives me a basis, and I want to compare these two bases. And so for that, what I'm going to do is that I'm going to move the snake from the bottom to the top by moving it, like sweeping it. And so there will be, I'm going to do this with two moves only. There will be one move that just moves the head. So here, that just happened. The head used to be here, and now, whoop, I move it here. And the second move will be the diamond move, which is on the next. It's easier to explain on the picture. So the diamond move is what happens in this formula, but don't try to understand the formula. Look at the picture. The picture is that it used to be that the snake goes left no, that's right. The snake would go right and then left, and you change that by having the snake go left and right. So in particular, you have a diamond here. That's why it's called the diamond move. Eh? So the snake it goes like from this to that. I don't think I can do that with my head. Anybody has a snake here? Okay. And and what you notice, so that's what the formula says. It's a, but so in terms of gray triangles, I used to go bloop 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 bloop, and now I go bloop 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 like that. Okay, and now there is the so each of these two snakes give me a basis, and we want to see how to go from one basis to the other, and there is a very simple formula. And notice one thing in this picture here, as I sweep the snake from this position to that position, he goes through this dot here. So that's a preferred dot in the triangle. It's this one here. And that dot, if you remember, gives me a triple ratio, one of those invariants. Okay, and so again, so when I have if I do a diamond move, like on the previous slide, I have this preferred point here, which give me a triangle invariant, one of those weird things. So the triangle invariant is, nope, that was the other one, is associated, you remember, to this hexagon here, if you remember, the triple ratio, triple ratio, sorry, it's in this talk. The triple ratio is associated to this hexagon here, centered at this point here. Okay, and so if the new stake gives me a basis with primes, the old snake gave me a basis with no prime, and there is a formula which enables me to go from the old basis to the new one. And so it's this formula, which is that, so this is at the kth step that we have this move. And so up to level k, nothing changes. And then at k, UK is replaced by the sum of UK and UK plus 1. And then after that, essentially nothing changes except that all these vectors are multiplied by a number, and that number is exactly this triple ratio invariant here. Okay, so how do you prove that? It's a computation. It's a it's a computation working in the white triangles. So let's go back here. Yeah, in this picture here, no, I went in the wrong direction, sorry. Around this dot here, you have these two white triangles, which give me two planes in the dual, and it's a computation in those planes. That's and then you have to relate that to the triple ratio. It's not hard, it's just boring. That's okay, but what I would like to emphasize is that the formula is very explicit. It depends on the triple ratio. And then also what's going to be important is that I have a plus sign here, not a minus sign. I also have a plus sign before UK, but usually we don't write it. And I have a plus sign before the positive ratio. That's why I put a minus sign before. That's what I would like to emphasize. Okay, so that's the diamond move when you're moving the inside of the snake. You can also move the head. So that's the boundary move, because that happens when you are near the boundary of the discrete triangle, or it's the snake head move. So you move the snake from the right to the left, and that's a picture with the triangle. And you do the same thing, blah, blah, blah. You have two bases, and there is a formula which is much simpler, and the proof is way, way easier because we don't have to use the double ratio. So that one is really easy as a computation. Okay, so there is a formula, and note plus and plus. Okay, and so, sorry, where am I here? I'm going too fast. I don't know, that's correct. And so remember, we're trying to prove that two flag triples that satisfy the maximum span property are equivalent under the action of GLN, namely there is a linear map sending one to the next, if and only if they have the same triple ratio invariance, which I repeated here. And then in addition, I want to show that every set of numbers can be realized as triple ratio invariance for certain for a maximum flag triple. Okay, so it's if and only if, only the part of only if, I did it last time. It just says that if there is a linear map sending EFG to E prime, F prime, G prime, then they have the same triple ratio invariance. So that doesn't change anything. Okay, the difficult part is if. Okay, so suppose that I have two flag triples that have the same triple ratio invariance. Okay, and then let's look at the snakes. And I take a sequence of diamond moves and boundary moves that sweep the snake from the bottom position to the top position by ploop, 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 ploop. Actually, more ploop, ploop with my right hand. There are more diamond moves than boundary moves needed. Okay, and so as I move like this, each position of the snake gives me a basis. And then we have that explicit formula to go from one basis to the next. And what was important here is that it was explicit and it depended only on the triple ratios. So in particular, as I move the snake from the bottom snake to the top snake, I see, I get the change of basis matrix from the basis associated to the bottom snake to the basis associated to the top snake. Okay, so that's good, but I would like you to notice one thing. Let's focus on the bottom snake. The bottom snake, well, it's at the bottom. And at the bottom, I have B equal to 0. So what you see is that there is no F. So this basis, it's a vector in this line here. So I have the two flags E and G, or in this case, E dual and G dual, if they pass into the dual. And I'm taking I have this line that is at the intersection of spaces between the two. And so it's like the situation of the ascending snake, the ascending flag and the descending flag. Namely, if I know these bases, I can completely reconstruct the flag E, E dual and G dual. That's what this says, that E dual, the k-dimensional space, is spanned by the first k vector in the bottom basis, and G, the k-dimensional space of G, is spanned by the last k-dimensional spaces of this bottom basis. And then similarly for the top snake, you can reconstruct E and F, or at least the dual. So E is not important because we only reconstructed it, but F is spanned by the last k vectors in the bases associated to the top snake. Okay, so if I know these two bases, I can reconstruct my flags E dual, F dual, G dual. Well, can do the same thing for prime. Hmm? Okay, and so now I have this basis from which I can construct E, F, E and G. This one from which I can reconstruct E prime and G prime. And then let's take any linear map from the dual to the dual, sending this basis here to that one. And so in particular, it's going to send E to E prime and G to G prime. Now, I know the coordinate, I know the change of basis matrix to go from this basis to the top basis. And I know the change of matrix to go the E prime from the bottom basis with primes to the top basis with prime. And I know that this change of basis matrix, it's explicit and it depends only of the triple ratios. So if they have the same triple ratios, it's the same in both spaces. And so if my map psi was sending the bottom basis here to that bottom basis here, it's also going to send the top basis to the top basis with primes. Okay, so in particular, because I could reconstruct psi from the bottom basis, so because I could reconstruct E dual from the bottom basis, it's going to send E dual to E prime dual. It's going to send G dual to G prime dual, and because I can reconstruct F dual from the top basis, then it's going to send F dual to F prime dual. So that guarantees that my linear map here sends the dual the spaces E dual, F dual, G dual in the dual space to E prime dual, F prime dual, G prime dual. Okay, but that was in the dual space. But now I go back in the dual, or I take the dual of the dual. Namely, I take the so I had this map phi from the dual to the dual. If I take its dual map, it goes from the space to itself, and it sends E to E prime, G. It goes backwards. Because dual spaces go backwards. It sends E prime to E, F prime to F, and G prime to F, which is what we want. So I showed to you that if two flag triples have the same triple ratio invariance, then there is a linear map sending one to the other, and it's this map psi dual, which was what we wanted. Eh? So, and that's really the highly non-trivial part of this whole story. Okay, and then I told you that I can realize any kind of invariance. And so another way to say, let's assume that I have a map associating a non-zero number to each dot in the interior of the discrete triangle. Then I want to find a triple ratio. I want to find a flag triple whose triple ratio at every ABC is x of ABC. That's what the statement said. What you do is that you reverse engineer the proof. Namely, you look at these explicit formulas telling you how to reconstruct E dual, F dual, G dual from the basis using the explicit change of basis matrices, and then blah 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 blah, and it works. So it's just based on a good understanding of this proof here. It's fairly easy. Okay, so the upshot of this is that result. I don't master the direction of the arrows. Where was the result? It's this one here, that if I consider maximum span flag triples in Rn, they are in one-to-one correspondence, or they are classified or parameterized by these triple ratio invariants, namely non-zero numbers, and there are n-1, n-2 over 2 such numbers. Namely, that's the number of dots in the interior of the discrete triangle. Okay. I've been going fast today. You guys should slow me down a little. So that was, yeah. Okay, triple. Okay, so we're done with flag triples. How about quadruples? Okay, so again, our question was given if a quadruple of flags satisfying the maximum path property, given another one, is there a linear isomorphism from Rn to Rn? That's a typo. Cut and paste, but cut and paste from the previous question about lines. Sending E to E prime, F to F. I'm sending all these flags here to those flags here. Well, we know that there are obstructions because if I have 4 flags, in particular, I have 3 flags, right? So I know that there are I can look at the triple ratios of EFG and the triple ratio of EFH, associate to numbers ABC with them. And is that enough? No, there is an additional invariant. Well, actually, you knew that because in the case of lines, we had a double ratio. So we have a double ratio. We have a double ratio here, where so for every AB, so if you have a flag quadruple like this, you have so you create a formula like this, wedge product like this. So what I would like you to understand, to notice in the formula, so it looks like all the other ones. It depends on A and B, with A plus B is equal to N. So that the sum of all these dimensions here is equal to N. So these are essentially numbers. And you take the double ratio. They are not numbers, they are determinants, if you want to compare that to what we did before. And what I would like you to notice is that there is a minus sign here. And that which is designed to make things nicer later on. Okay, so as before, this is non. If the actually we only need here EFG and EFH to satisfy the maximum span property. That's going to help us to guarantee that these numbers here are non-zero. So this is well defined. And again, each quantity appears once at the top and once at the bottom. Look like that's true for EA, FB minus 1, but also G1 here appears here also. So as before, that guarantees that it doesn't depend on choices. Same idea as for the triple ratio. And so there is a theorem which is that given 2 maximal span flag quadruples in Rn, there exists a linear isomorphism sending one to the other, if and only if, well, they have the same triple ratios like this, and they have the same double ratio like that for every ABC, A prime, B prime, blah, 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 blah. Okay. And the proof is actually this is much easier than the previous one, because I see I have time to finish this. So only if is as before, if using determinants essentially. Right? And the if, well, suppose that they have the same invariants. Well, by the case of flag triples, if they have the same, if E, F, G and E prime, F prime, G prime have the same invariance, I know that there is a linear isomorphism sending E, F, G to E prime, F prime, G prime. And similarly, with the other flag triple, there is another linear isomorphism psi sending E, F, H to E prime, F prime, H prime. And if it happened that phi is equal to psi, if the two linear isomorphisms are the same, then I would be done. Well, except that there is no reason, right? And but what you notice is that phi and psi, they send E to E prime, F to F prime. And you remember, when I have two transverse flags like E and F, they determine a line decomposition. So I have a line so phi and psi, they both send elements in the line decomposition associated to E and F to the one associated to E prime and F prime, meaning that there is because these are lines, the one is a multiple of the other, so there exists a number lambda k such that the restriction of phi of psi is the same as lambda k times the restriction of phi. And then once you have that, you compute, you find that this triple ratio here is this double ratio here is this double ratio multiplied by the ratio like this. Okay, now if you know, it's a very easy computation. And so if you know that, then and if you know that the double ratios are the same, that means that lambda a plus 1 is equal to lambda a, so they are all equal. Well, so they're equal to some lambda. Yeah, and so that guarantees that psi is, so on this line decomposition, on each restriction, you have that psi is lambda phi, and therefore it's true everywhere because they span the whole space. Okay, but if psi is lambda phi, and if phi sends h to h prime, then phi also will send h to h prime. So blah 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 blah. That's it's a very simple argument here. Okay, so we seem to have exactly the same result as before, right? This seems to nope, that's the other one I was going to ask. Well, I proved that two flag quadruples are the same if and only if they have the same invariance like this. So you have a one-to-one correspondence. The only problem is that there is a missing statement here, which says that every set of numbers I can realize by as double and triple ratios of a flag quadruple. And actually, if I state like this, it's very complicated. And so, that's the question. Which numbers can be realized? And so, what the statement says, let's do it in practice for n equals 3. Okay, so you do it by hand. N equals 3, it's not hard. And you find that, so these are the only possible ratios. So you have numbers, you give yourself numbers x11, x11 prime to realize the two triple ratios, and x21 and x of 1t to realize the double ratios. And they are realized if and only if these conditions are satisfied. And also, these are non-zero numbers, so they are also different from 0. And I don't know what you think of it, but it's ugly. In particular, these conditions here. And it's only for n equals 3. So if you try n equals 4, it's way, way more complicated, unless you restrict attention to positive numbers. And the answer is much simpler when we do positive numbers. That will be the topic of today is Tuesday, tomorrow. Okay, that's it. Thank you. Oh yeah, yeah, I'm 5 minutes early. Is that okay if I finish early? Yeah. No, 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 no way. I mean, even these ones are actually not that easy. So if you want to play with it, yeah. However, so what I want to emphasize is that if these numbers are positive, this condition is always satisfied. And this one too. Eh? So positive is nice. Okay, that will be later. The what? Oh, partial flags. Oh, yes. So it's incredibly complicated also. So Anna Winhart had a student, Marek Pfeil, who was working a little bit on that actually. So she came to visit me and we thought about it. It's very complicated. Uh, uh, oh, not that I know of. But you have to realize that in this whole field, I am a dumb topologist. No, seriously, the people who were born as Lie theorists have much more intuitions than what I have for these kind of things. So I'm trying to learn from them. So usually they have the right ideas. But my guess is that it's not very simple. But these are good problems. In particular, in particular with these piano sort. Yeah. Yeah. Yes. So I'm going to repeat something that I don't understand. It's the following. So these snake sweep sequence of boundary moves and diamond moves. Actually, there is a way to understand that in terms of so let's try a maximum word in the while group. Okay. So you have in the while group, you have this element which essentially is multiplication by -1, and which you can realize it as a composition of reflections in the while group. And there are many possible reflections. Um, uh, and if you choose one such decomposition, so in this case, the while group is the symmetry group. And so you have these, this element, I think, is just reversing the order. So you can represent it by a composition of transpositions. But there are many ways you can do that. And there is sort of a one-to-one correspondence between the snake sweeps and this decomposition of these orientation reversing element as a product of transposition. Okay, I don't understand that. Again, the Lie theoretic people are the ones who have the right ideas there. Yeah. So that's we get an idea. And then just stop it. Then gives you a bunch of plans. Yeah. So what's the stand of it? Which lines? I'm sorry, because we have way too many here. And you're in the dual space, right? Yes.
But let's say I don't start at somewhere along the bottom.
Yes.
Starting point is here, I in the
Yes.
okay, then now I do the same like this.
You're going to have a hard time getting a family of lines that span the dual space.
Right, we'll get somebody span a subspace.
You're going to span the subspace, yes. It's a good question, yeah. Yeah, I understand what you're saying. There is no guarantee